Okay, so our first main definition is about a principal ideal domain. Sometimes we'll just say PID. And what this is it's a domain. So commutative ring without zero divisors, such that all ideals are principal. That is, if you have any ideal in this domain, there exists a principal generator. So you may have written your ideal as generated by more than one element. So for example, in Z, you can look at the ideal generated by like 6 and 4. So it looks like it's generated by two elements. This is like 6x plus 4y. X and y are in Z. That's the definition of that set. But really, we saw it's principally generated by two. In fact, our first theorem is that Z is a PID. That is, all ideals in Z are principal. All right, so let's go ahead and prove this. Proof. The zero ideal is just zero. It's principally generated by zero. And this tells us that we can assume that if we have an ideal that we want to show as principally generated, it's non-zero. It's got a non-zero element in it. And when you show something as a PID, I mean, technically we need to include the zero ideal, but the zero ideal is always principally generated by zero. So in the definition of PID, we could even say, hey, if all non-zero ideals are principal, because the zero ideal is always principal. But nevertheless, we've read it out. Let's consider I be a non-zero ideal. And let's set S to be I intersect the natural numbers. So that is, we're looking for the positive elements of I. Since I is not zero, there exists some A not zero in I. If A is bigger than zero, then A is in S. And if A is less than zero, well, then negative A is in I, and therefore negative A belongs to S, right? Because I absorbs multiplication by ring elements. So I can multiply A by -1 to make it positive, and then now we have something in this. So in particular, S is a non-empty subset of N. What do we know about non-empty subsets of the natural numbers? Well, the Well ordering principle, which I'm just going to write WOP, S has a least element. I'm going to say D is in S. We claim that that least element is the principal ideal generated by that least element is all of I. Well, certainly D is contained in I. The principal ideal generated by D is contained in I, as D is in I. So all multiples of D are in I. So the difficult part is the reversed containment. Or it's not difficult, but the more involved part's the reverse containment. So to see that I is contained in D, let's take some, let's see, we're in the integers. So let's take some B in I. And we want to show that B is a multiple of D. So what do we do? Well, we approximate it as a multiple of D. That is, we're going to use the division algorithm to find Q and R such that B is dq plus R, where R is between 0 and D. So 0 less than or equal to R less than D. Then R is B minus dq. B is in I. D, all the multiples of D are in I. So this whole thing is in I. But D is the least positive element of I. By the well-ordering principle, it's the least one. That's how we found it. So R, being an I, cannot be positive. So R must be 0. 0 is neither positive nor negative. So B is a multiple of D. It's in the principal ideal generated by D. Thus, that's the reverse containment. So I is generated by D. Fantastic. That's it. We did it. It's the end of the proof. Z is a PID. And let me just note something here. This actually tells you how to find the principal generator. So given an ideal in Z, it is principally generated. There's more than one because associates generate the same ideal, but it is principally generated by the least positive element in it. Why do we know that? Well, that's what the proof showed. We find the least positive element, and that's a generator. It's also generated by its negative, so it's not like there's only one, but the proof actually gives us a recipe for finding the principal generator.